So here we go. I open a new model. There we go. The time step. Always take something that is at least a fourth of the time step of the smallest time constant in your model. And I happen to know that this is 1 month in this case. And here it's always a good idea to use a good integration method. I'll come back to that next week. As for now, just take Rumakuta 4 or something like that. So the exercise is the following. The monthly change in the total quantity of cocaine in a country depends on the monthly quantity of cocaine imports, the monthly quantity of cocaine used and the monthly quantity of cocaine confiscated by the police. In a highly simplified model, we assume that 3,000 kilograms of cocaine is used per month. The import of cocaine is constant and amounts to 4,000 kilograms per month, and the monthly quantity of coke confiscated by the police is equal to 10% of the cocaine in the country. Suppose there was an initial amount of 3,000 kilograms of cocaine in the country. So that's basically the question. Well, you can address this in at least several different ways. We're interested in the dynamic behavior over time. So, well, either we could just make a closed loop diagram, for instance, coke, the more imports we have, the larger the amount of coke in the country will be. On the other hand, we have use, so the larger the cocaine use is, well, the smaller the amount of coke in the country is going to be. And then apparently we also have busts, and the more coke there is in the country, since 10% is busted, we have a feedback loop here. So the more coke in the country, the more busts, hey, the less coke in the country. So this is a negative feedback loop. So let me add the symbol here. This is going to be a negative sign. There we go. Now, knowing from part 1 of this week that a negative feedback loop in isolation shows converging behavior, we just know now that we get converging behavior here towards a particular value. However, our causal loop diagram does not allow us to, know what that converging, what it converges to. So what the let's say the goal value is going to be. A simulation model could do that, or mathematics could do that. And just again to give you some connection with mathematics, in this case the differential equation is of course the change in coke over time is equal to imports minus use minus busts, but busts is equal to the confiscation rate times the coke in the country. So this is our differential equation, and you can use this or the integral equation to calculate the equilibrium value this system will converge to. Now, let me make the simulation model quickly. It takes almost as much time, and it will immediately give you the outcomes. So I'm going to use a stock variable for the amount of coke in the country. I will use an inflow, so I click outside and then inside my stock value for the imports, and then uses is an outflow. Use of coke is an outflow of the coke in the country, and the busts, confiscation, is also an outflow. And as I said, we should actually try to have all initial values and all auxiliaries and all constants as much as possible outside of these flow equations so that the model becomes understandable. So I'm going to add the confiscation rate as a normal auxiliary or constant, and I will now add all the additional causal links. Don't forget, your inflows and outflows are also causal links. Imports is a positive causal link from imports to coke, and there's a negative causal link from use to coke, and there's a negative link from coke to busts. Now, we also know that there is a positive causal link from coke to busts. The more coke there is, the more busts, and given the confiscation rate, the less cocaine there will be in the country. So here we have a negative feedback loop. And on the other hand, there are no further links between imports and use. So if I click on the equations button, then I can actually add the values for my model. In this case, my integral equation is already here. It's the integral of imports minus bus minus use, and I just need to add the initial value, so that is initial coke, and the units, in this case kilograms. So initial coke was 3000 kilogram. Okay. Imports, well, here we have 4000 kilogram per month. Use is 3000 kilogram per month. Confiscation rate is 10%. Always use 0.1, I mean a fraction, if it's a percentage value. But it's not just 10%, it's 10% per kilogram that is available in the country per month. So this is actually in kilogram per month, or 1 over month. If you multiply that by kilogram of the variable coke, then you actually get kilogram per month here, which is exactly the units that you need for your busts, which consists of coke times the confiscation rate. So here we have kilogram per month. In terms of units, just remember that the units of your inflows and outflows connected to a particular stock by means of flows, these flows always have the units of the stock divided by the unit of time. So now we have our first model. I can simulate it. If I click on set up a simulation and give it a particular name, then I can simulate it, run the simulation. There we go. And I can visualize with a graph the type of behavior. And indeed, we get some sort of converging behavior. Now, my time settings are such that I do not see the full convergence. So what I'm doing now is change my settings a little so that we can actually see the convergence over time towards a value of 10,000. Let's just test whether that is true if we start from a higher value as well. So now I'm changing my initial coke to, let's say, 13,000, and if I simulate then and visualize the behavior, then you see that in both cases I get convergence towards 10,000, which we already knew from the closed loop diagram and from the equation. However, from the closed loop diagram we were not able to derive the precise value it was going to converge to. Now we know with our simulation model. So the remainder of this week really consists of practicing with very small models, and that's the end of week 1. So by the end of week 1 you should be able to make very simple models and draw the causal loop diagrams and get an idea of the equations, and that's all. From next week on it will be much more difficult because we will look at specific functions that can make our simulation models much more realistic.